Hey everybody, I hope this video finds you well. In today's video, we're going to be finishing up section 4.6 from your textbook, which was introducing you guys to the concept of a basis of a vector space. To do this, we're going to do a couple little odds and ends to finish up this section. First, we're going to do a couple comments or a couple little extra facts about bases, specifically about how the basis of a subspace relates to the basis of a vector space. Then after we have that discussion, we'll actually take a look at some examples of determining a basis for a given subspace. When we do those examples, they'll actually feel pretty familiar because back when we were first introducing you guys to the concept of a subspace and a spanning set, we actually did determine the basis of a subspace. We just didn't have the terminology of a basis available to us yet. So those examples, while sort of with fresh terminology, will seem pretty familiar. And then we'll end this sort of section by actually showing an example of a vector space that is infinite dimensional. In other words, that it does not have a finite basis. And we'll do that by looking at one of our sort of common vector spaces that we haven't discussed for a while, which is the space of all functions that have an infinite amount of derivatives. So let's get right in and talk about a few basic comments on bases, then sort of bases of subspaces versus bases of vector spaces. So our first comment here is if S is a subspace of V, then the dimension of S is less than or equal to the dimension of V. And if the dimension of S is exactly the same as the dimension of V, then S is actually equal to V. So we're not going to prove this statement, but I hope that it makes some sense to you guys. What this is basically saying is that if S lives inside of V, then certainly the dimension of S cannot be larger than the dimension of V. And specifically, if the dimensions are the same, well, then the spaces are actually the same. Now, this should make sense in the case where V is finite dimensional because, well, then the dimension of V is exactly as we've defined it in the past. But this concept actually even makes sense in infinite dimensional spaces, right? If V is infinite dimensional, then subspaces of it might be finite dimensional, but certainly they would still be smaller in dimension, right? The second comment here, which, is not going to be super essential for our course, but it is an interesting concept in general, and we'll discuss it a little bit in some of our examples, is that if you have V1 through Vn as a basis for a subspace S of a vector space V, then you can extend this basis, that is a basis for the subspace, into being a basis for V by just tacking on some extra vectors. In other words, what this is sort of saying is if these guys form a basis for a subspace, you can use these plus some other ones to form a basis for the overall vector space. And of course, how many vectors will you need to add in? Well, it'll be the difference between the dimension of V and the dimension of S, because of course that's how many sort of missing vectors there must be in terms of the basis. So if you look in your textbook, you can find some more formal proofs of these, but I do hope that just from our discussion so far, these two comments should generally make some sense here. So let's get into looking at some examples of finding bases for given subspaces, and then also have a brief discussion of how we could extend them to bases overall. So let's go ahead and take a look at that. So for our first example, we're going to return, I think, to a subspace that we've already discussed beforehand, and we're going to try to determine a basis for this, and then use this to determine the dimension. So the subspace we're going to talk about here is the space of matrices that are symmetric, A equals A transpose, and that have a trace equal to 0, and happen to be 3 by 3 square matrices. Now, notice that in the phrasing of the question, we're already being told that this is a subspace. You guys should think back, though, to when you learned about subspaces in 4.3 to remember how you prove something is a subspace. Remember what you would need to do is you would need to show that this set here is closed under both addition and scalar multiplication. In this case, that would mean that if you add two matrices that are symmetric, it would remain symmetric. And if you add two matrices that have a trace of 0, the trace would remain 0. You'd also need to show that if you scalar multiply a symmetric matrix, it would remain symmetric. And if you scalar multiply a matrix with trace of A equal to 0, it would remain having a trace equal to 0. Now, in the phrasing here, we're already assuming that those things are true because we told that it's a subspace. So we just want to determine a basis for the subspace. And then, of course, the number of vectors in that basis will tell us the dimension. So the easiest way to do this is to try to determine what is a general element in S, right? If we can figure out what the sort of general element in S looks like, then we can figure out what is necessary to sort of generate those things, which will be our basis. So if we think about it, right, if we think about a sort of element in there, it's going to be 3 by 3, and we have to make sure that we satisfy these properties that it's symmetric and that its trace is 0. So if we think about that, right, we could say, okay, we could put anything we like in the 1, 1 component. And we could put anything we like in the 1, 2 component, but of course, whatever we put here immediately also has to be placed here. We can put whatever we like in the 1, 3 component, but then of course we have to place that here to guarantee that it's symmetric. We can place anything we like here, because those are only 2 of the diagonal elements, but once we place those 2, this element right here is determined for us because it has to guarantee that the trace is going to be 0. Then, of course, we can place anything we like here, and it has to go there so it remains symmetric. So that's what a sort of general element in this subspace looks like, right? We get the free choice of A, B, C, D, and E, and these other components are determined for us. So how do we translate this into a basis? Well, remember, for a basis, we want it to span this, but we also want it to be linearly independent. So there's a very easy way to do that if you know what a general element looks like. What you do is you simply let one of these free variables be equal to 1 and all the other ones be equal to 0. What that does is it assures that you can span this, because if I say let A equal 1 and everything else equals 0, well then I know that when I want to build this general element, I just need to do A times whatever matrix that looks like. Furthermore, if I let each component be 1 and everything else be 0, I'll guarantee that these things are going to be linearly independent. So let's go ahead and see what that would look like. So the basis here would be, well, it looks like it should be things like 1, 0, 0, 0, 0, 0, 0, 0, negative 1. Then we should have something like 0, 1, 0, 1, 0, 0, 0, 0, 0. We could have something like 0, 0, 1, 0, 0, 0, 1, 0, 0. Looks like we should have also something like 0, 0, 0, 0, 1, 0, 0, 0, negative 1. And then finally, looks like we should have something like 0, 0, 0, 0, 0, 1, 0, 1, 0. And that right there would be a basis. Now, if you wanted to prove that this thing was a basis, what you would need to do is show that these 5 things would span this. That would be very easy because, well, we literally made these by making sure they would span this. And then you would need to show that they're linearly independent. Now, that would take a little bit more work, but it's not hard to do. That would be only necessary if you needed to prove that it was a basis. But I think it's pretty justifiable if we're just trying to figure out a basis, once we know that general element, to just see that this is going to work for us. What does this tell us then? Well, this would tell us that the dimension of S, right? Well, there are 1, 2, 3, 4, 5 vectors in here. So the dimension of S is 5. Notice that this also satisfies the first comment we made at the beginning of this video. We know that the dimension of this vector space overall is 3 times 3, which is 9. And of course, our subspace is equal to 5. The dimension is equal to 5, which is less than or equal to the dimension of the overall vector space. Now, could we see how to extend this? Well, we would know that to extend this to a basis for M3, we'd have to add in 4 more matrices, and we'd have to make sure that those other 4 matrices would be linearly independent from these 5 that we already determined. If we could do that, if we came up with 4 more matrices that are linearly independent from these guys, then those 4 plus these 5 would give us a basis overall for M3 of R. Okay, so that's basically showing you guys, given a subspace, how to sort of think about the general element, use the general element to determine a basis, and then use that basis to talk about the dimension. Let's try one more example of that. All right, so we want to consider the subspace, this time of polynomials, that have the property that they have a root at 1, so p of 1 equals 0, and they have a property that p of negative 1 is 0. So they have a root at x equals 1 and a root at negative 1, and they live in P4 of R, which of course means that they are degree 4 or less polynomials. So we want to determine a basis for the subspace and use this to determine the dimension of S. So let's think about what the general element would look like in this case. So we know P of X has to have a root at 1 and at -1. So it has to have a factor of x minus 1, and it has to have a factor of x plus 1. But it also has to live in P4. Now this is going to contribute a degree 2 term, so we can't go beyond degree 4. So all that would remain is the option for some degree 2 p's, meaning something like ax squared plus bx plus c. If you think about that, this general element assures us that we have the two roots that we want, and it assures us that since we have degree 1 times degree 1 times degree 2, we will be inside that degree 4. Now, if you want to actually expand that out rather than writing it in sort of a factored form, I suppose you could recognize that that is x squared minus 1 times ax squared plus bx plus c. And you could actually multiply that out so you could take a better look at it. I guess you would get something like ax to the 4th plus bx cubed plus cx squared minus ax squared minus bx minus c. So this guy would look something like ax to the 4th plus bx cubed plus c minus ax squared minus bx minus c. Okay, so what would be our basis here? Well, we'll do the same sort of trick. The basis would be first, let's let a be 1. So we'd get something that looks like x to the 4th minus x squared. Then let's let b be equal to 1 and everything else be equal to 0. So it looks like we get something like x cubed minus x. Okay. And then let's go ahead and let c be equal to 1. And it looks like we get x squared minus 1. So those three polynomials would generate everything that is going to be degree 4 or less and have these roots at both p of 1 equals 0 and p of -1 equals 0. So this tells us then that the dimension of S in this case is equal to 3. Does that make sense that we're getting a dimension of 3 here? Well, it should make sense because overall we know the dimension of P4 of R is 5, and this is certainly less than or equal to that. So this makes sense that we're getting a smaller dimension because we're working with a subspace here. Right? Also, do notice that all three of our basis elements also clearly have the properties that we mentioned in the subspace, right? So it makes sense that they would generate everything like that, right? This guy definitely has roots at 1 and -1. This guy has roots at 1 and -1. And this guy has roots at 1 and -1. Okay, so the idea here, right, again, is that we're not proving that these things are bases. Again, to do that, what we would have to do is go back and show that this will really span this and that these guys are linearly independent. But again, since we had the general element, we can sort of make that assumption by realizing, well, if I take each free variable, let them be 1 and everything else be 0, that's going to guarantee the spanning, and it's also going to make sure that we're linearly independent. Of course, that approach hinges on being able to figure out the general element. All right, let's wrap up this section about bases by quickly going over an example of something that is infinite dimensional. So to do that, what I'm going to do is consider, then show you guys how you would, basically demonstrate to somebody that this space, the set of functions that have an infinite amount of derivatives, is an infinite dimensional vector space. Okay? So the way I'm going to do this, right, is I'm going to claim that in this space, the set 1x down to x to the n is linearly independent for all n. Okay? In other words, what I'm going to do is I'm going to show you guys that in this space, right, these polynomial functions, 1x all the way up to x to the n, are linearly independent for all n. Now, the idea here is that inside of this space, there are tons of other functions. Sine of x and cosine of x and e to the x and tons of combinations of x, so crazy things like e to the 5x plus sine of 3x minus x to the 5th, anything that has an infinite amount of derivatives is in this space. But I'm going to claim that even just this set is always linearly independent. And what that's going to show you is that the dimension of this would always have to be larger than this amount of vectors. And of course, the amount of vectors here, right, this has n plus 1 vectors in it. So since the basis would always have to include at least these things, and this is true for all n, that would demonstrate to you guys that there is no finite basis. Because even just to talk about all the polynomials, you would always need at least n plus 1 vectors. Now, I could just say, well, we know these n plus 1 vectors are linearly independent, like from what we talked about with the polynomial space. But generally, when we work inside of any of the sort of functional spaces, rather than just the polynomial space, we like to use the Wronskian. So let's consider the Wronskian of 1x down to x to the n. And if you think about what that Wronskian looks like, we know it's going to be the determinant, where you have 1x x to the n. And then we take derivatives. So we'd have something like 0 and then all zeros, right? Because the derivatives here would be, once you take the derivative of this once, it's going to be 0 and it'll continue on. Whereas here, it would be 1 and then all zeros. And then here would be something like nx to the n minus 1. And then if you continue doing that, you'd keep taking derivatives, and it shouldn't be too hard to realize that this would come out as n factorial, right? Because if you keep taking derivatives, eventually when you get down to here, you've taken all the derivatives and you've gotten down to n factorial. Well, if you think about this then, what do we know about this sort of matrix here? Oh, well, this guy, right, is an upper triangular matrix, right? What that means is that the determinant here is going to just be the product of these elements. But it shouldn't be hard to see that everything on the diagonal is just going to be a constant. This is going to be equal to some number. Now, I don't know what that number is going to be. It's going to be a little bit messy. It's going to be like 1 times 2 times times n factorial. So it's going to be like 1 times 2 times 3 times 6 times 24, so on and so forth. So it's like a factorial of factorials. But the point is it's a number, and it's not equal to 0. So these functions are linearly independent. What that means is that any basis for C infinity must include at least all these things. So that means that any basis would need to have at least n plus 1 vectors for all n. So that means any basis for this must be infinite, which means it is an infinite dimensional vector space. Now, interestingly enough, right, if you guys think back to what you learned back in like 191, you actually sort of saw that any function that has an infinite amount of derivatives actually can be represented as an infinite amount of polynomials. And that was the concept of a Taylor series. So if we were to expand our idea of a basis to include an infinite set of vectors rather than a finite set, then the infinite set of all polynomials, 1x, x squared down to x to the n for all n, is actually a basis for all the functions out there. In other words, every function that has an infinite amount of derivatives can be written in terms of 1x, x squared, all the way down to x to the n. So this is sort of an interesting idea, right? That you could extend the concept of a basis to infinite dimensional spaces if you were to allow yourself an infinite dimensional set. But in this case, all we wanted to show here is that it couldn't have a finite basis, so this guy is an infinite dimensional vector space. To be honest, we won't work with infinite dimensional vector spaces very much in this class, but just wanted you guys to see at least one argument for why they exist out there. All right, that's going to finish up our discussion of bases. In the next video, we're going to talk about how you represent elements in a vector space in terms of a particular basis.